Hi, I'm Rena, and in this video, I'm going to walk through k-means clustering step by step in a Jupyter Notebook, from intuition to math to code. We'll cover how the algorithm actually works, why distance matters, and how principal component analysis, or PCA, can help us visualize in higher dimensions. If you're learning data science or machine learning and want a clear, practical explanation, this video will give you a solid foundation that you can use in real projects. So, how do we segment data in a space? Let's see how the k-means clustering algorithm can help us out and what the steps are. Before we can begin, we must select the number of clusters. Let's call it k. Our first step will be to initialize centroids randomly in the space. Let's allow these red triangles to represent the centroids in our space, and we'll set k equal to 3 clusters. Once we have them, we will assign each data point in our space to its closest centroid. Once we have assigned each data point to its appropriate cluster based on its closest centroid, we will now update each centroid to its cluster mean. So what does that mean? We're going to take our existing centroids and we're going to move them over to now be in the center, but it is really the average of the data points. So now that we have updated each centroid to its cluster mean, we must repeat the steps until we reach convergence. We can iterate through this process until the centroids stop moving altogether. Hope that demonstration helped, but I have also created this animation with Python code showing several iterations of the k-means clustering algorithm as the centroids move based on the data points that create its cluster mean, and the data points assigned to that cluster are updated at each iteration. Now we can get into the Jupyter Notebook and begin coding this algorithm. Here we are in our Jupyter Notebook, where we will implement our k-means clustering algorithm using Python code. So first, we'll import some Python libraries to help us out. You'll notice that this one, sklearn.cluster import k-means, that is the one we will be using to train our model as we go along. So the dataset that we're working with today is from Facebook statuses. It includes features about what type of status is being posted. The video, photo, status, or link are our options. And there's plenty of other features that we can use to segment our posts. So we have number of reactions, number of comments, number of shares, likes, loves. We will see how the different distributions of these features impacts how clustering works. So we see the status type video and photo have the highest values. There are 4,000 photos in total, and we are plotting this against the total number of reactions. What's interesting in this plot is that even though the number of videos that we have is less overall, the number of videos with reactions over 200 surpasses that of photos. When it comes to a large volume of reactions, videos are the number one spot. As you'll see in this data, we have the status type of video, photo, link, and status. This is very valuable information that will prove to help segment the data. However, we cannot pass a non-numerical value. We have a few options. We can either encode that feature and map video to 0, photo to 1, link to 2, status to 3. However, that implies that there is some ordinality to this feature, that photo is somehow greater than video or vice versa. But we know that that's not true. So in these cases, we would take the feature and one-hot encode it. So I'm doing that here with this pd.getDummies function. And basically I will pass status type and it will create a new input feature for each of those. As you can see here, these features, status link, status photo, and it is either a 0 or 1. So if it was a photo, this row is a photo, we can see that it gets a value of 1, and if it's not a photo, it's a 0. So now we have these 4 new input features, and we will delete the previous status type before we train. Another important statement is that in this data set, we have this feature called status published. And this is a date time feature. Date time features are actually really cool, and we can extract 20 to 30 or even more features just from this one input feature. For today, We will be focusing on the k-means clustering algorithm, so I will not be getting into time series wrangling. However, if you are interested in learning how to take a single date time feature and extract many different other features about seasonality, the time of the year or week, and other factors, please let me know in the comments below. I would be happy to get into date time wrangling and time series analysis. But for this notebook, we will be focusing on k-means clustering. Okay, so let's get some clustering intuition. We did look at some drawing about grouping data into clusters, but let's look at a quick little scatter plot in one dimension, right? The simplest form of data that we can look at is just one dimension. Perhaps it's the number of reactions. Okay, so in general, the number of reactions spans across 0 to 5,000. How would we segment this? Anything is up for grabs, really. We don't have to use k-means clustering. What if we plotted a vertical line just to make some separation in the data? Maybe to the left of the red line is one group and to the right is another group. But is that strategic enough for us? Maybe we find these little gaps in between and call those segments. Maybe between each red line is a group. We can employ more strategic methods. Let's gain more intuition. So if we go into two-dimensional clustering, we will now plot between two features. Let's say we have the number of likes and the number of loves. And we can look at the behavior of different status types. What's interesting is that video and photo kind of make clear groupings. As we saw earlier, the links and statuses have far fewer posts overall, so they won't show up as much on this plot. But it is still interesting to see that as the number of loves increases, right, we stop seeing photos keeping up with videos. That tells us that videos far surpasses any other status type when it comes to the number of loves. Number of likes, we see photos getting higher volumes. However, if we look about 1,500 and go across, to be honest, the videos are actually keeping up. So perhaps I can plot that for us to see. So overall, videos are pretty much keeping up with the number of likes that photos have until a certain point. So if I did 2,500, even less than that, the videos don't keep up anymore. So perhaps this will be a factor in our clustering. These might be important features that the clustering ends up dividing on. Although it does get the average across the entire space, this set of features definitely will have an impact. So using the line method like before, what if we start to plot vertical lines? What if these were our segments? This doesn't look too bad to me, actually. This could be an immediate segmenting if we didn't know about the k-means clustering. But what could be even better is we see more of a divide down the diagonal. Perhaps we draw a straight line. And perhaps we change the slope of the line. And we mess around with it until we find a division that makes sense to us. I think this is a good segmenting of data, but this would require a lot of human effort for us to look and see if the line matches up quite enough, and perhaps we would then employ some distance measuring to see how well it's doing. But why would we take all of our precious time and attention doing that when we know we have the k-means clustering algorithm amongst many other clustering methods, or perhaps there will be new clustering methods in the future? So we want to employ our most strategic method of clustering at any given time. Just to drive home the point of our clustering in higher dimensions, we take a look at this three-dimensional plot and we start to see that we can't just draw straight lines anymore. We can't really visualize beyond this. So in 3 dimensions, we might use a flat plane to divide the space. What about in 4 dimensions? 5. What about 1,000 dimensions? At a certain point, a human cannot sit and look at a plot and draw lines to segment it. That's why we use the k-means clustering algorithm, because it can employ a set of steps that work in higher dimensions. And we'll also discuss what happens in higher dimensions to the k-means algorithm and what happens to Euclidean distance in higher dimensions. At a certain point, it does break down. For our k-means algorithm, I first would like to show how it works on only 2 dimensions. As you'll see in the comment here, I wrote that x is only 2 dimensions. We have our x feature and our y feature. Later, we will use all of the features, but I just want to continue to drive home the point of going from a lower dimensionality to a higher dimensionality and what happens and what we have to look out for in these cases. In this case, we will train our k-means algorithm, pass the number of clusters, and plot the results. So here I'm just selecting 3 clusters randomly. In a little bit, I'll show how to pick that number of clusters. So we'll use our favorite 2 features again, number of likes and number of loves, and we will see how the k-means algorithm segments the data. If we were using our human drawing method, we might have created vertical lines going up the number of likes axis to divide, and we could have gotten quite a similar result. However, this does create a little bit more granularity than our drawing could have. This is in 2 dimensions. As we've been stating, the measurement of distance in Euclidean space is very important for k-means. If you recall, each data point is assigned to its cluster based on calculating the distance to each centroid and then being assigned to the centroid that is closest to it. Recall the equation for distance in Euclidean space. You take the distance as the difference between 2 points in their x-axis and their y-axis, square the values, add them, and then take the square root. We can do this in any dimension by increasing the number of factors. However, as the number of dimensions increases dramatically up to 1,000 or more, we start to see the meaning of the Euclidean distance metric breaking down, not really making sense anymore. With only a few features, it's still fine. With 10 features, you can use the equation for Euclidean distance and it'll work quite well. So if we have high dimensionality in our dataset and we'd like to reduce it to a lower dimensionality that is easier to work with, and where Euclidean distance will work well, we can use something called principal component analysis, or PCA. So PCA is where our data comes from a high dimensionality and we map it onto a smaller space. Typically, we want to see it in only 2 or 3 dimensions because it is easier for our human minds to understand. So principal component analysis reorients the feature space to span the directions of greatest variance. We will scale our data before PCA and k-means because both of them depend on distance and variance. Here I'm scaling the data, and before I do that, I get rid of any features that are non-numerical. So in this line, with the fit transform, we will be performing our principal component analysis, taking our scaled data. So here we will take PCA both without scaling our input data and with scaling our input data, and we will analyze how much of this feature space has been covered. We can look at the variance covered by each principal component and add them up. Without scaling, our principal components cover 99%, but with scaling, our principal components only covered 44%. As stated before, principal component analysis is useful when the dimensionality is very large. In today's dataset, we only have about 10 features. So reducing to 2 principal components would discard a substantial portion of the information. So today we will not be using PCA for training, but we can still use it for visualizations. Here is a scatter plot of our scaled data mapped onto 2 principal components. We can see it has quite a spread. So let's move on to clustering. As stated, we will be training on our input data scaled without using PCA. However, we will plot the results using PCA so that it is easier for us to visualize because we cannot visualize a 10-dimensional plot in Python, not yet anyway. In this function, we will be training our k-means algorithm on n clusters using input x. And then you'll see PCA here, but remember it's not used for training. It is only used for our visualization. So let's go ahead and do that. Take a look at our scaled data. We have 13 input features and 7,000 rows. Let's go ahead and train and plot. I've randomly selected 6 clusters. And this is what it's showing us. There might be too many clusters here. This brown set of dots kind of overlaps with the orange and the blue. It doesn't really make much sense to me to have this many clusters, but we will still carry on and use it for a bit of analysis in this spider plot. So let's take a look at this spider plot. Let's try to see the ones that have the highest in video are purple, which also has the highest in reactions and wows and shares, which was to be expected by our previous data analysis. And this spider plot shows the breakdown of the engagement after we've done our k-means clustering. What if we try a different value of clustering? I'd like to see photo is in orange, video is green or red. So videos continuously beat everything out. And the status in blue is getting a lot of likes. We can analyze this as much as we like. I will include this code on my GitHub for anyone who would like to recreate this project. So now how do we choose the optimal number of clusters? We use a value called inertia and an elbow plot. This is the standard in finding the optimal number of clusters for k-means. Typically what we want to do is look at the inertia metric over the number of clusters and find a point of inflection where the benefit reaches somewhat of a marginal gain. Basically, you want to see a point where the dramatic decreasing tapers off. I'm kind of seeing it around 3 to 5, potentially even more. So let's start with 3 clusters and see what that does. Visually in 2 principal components, which remember, this is only a slice because our principal components don't encompass the entire data set. From this point of view, looks like the blue is overlapping with the orange. We can also look at the distance to the centroids and optimize on that. The maximum distance is 43. And then we have a distribution. So the number that are less than 1 are 4,000 out of our 7,000. And we are plotting this distribution. So there's a good distribution of the data, mostly being close to its centroid. However, I would like to try increasing to 4 clusters. The max distance changed minimally, so it definitely tightened up at least 1 cluster area. So the 4,000 now has gone up to 4,600. Just for fun, let's see what happens if we keep increasing those clusters. Not much of a change from 3 to 6. Only about 600 data points have been brought closer to its centroid with a distance less or equal to 1. And just for fun, let us try 7. Okay, between 3 and 7, we've gotten 1,000 more data points that are within 1 unit of its centroid. Let's see if we did between 2, and we have 7 centroids, 7 clusters, so it has 6,000 out of the 7,000. And if we brought that back down to 3, oh, there really is not much of a difference between using 3 clusters and 7 clusters. In this case, I would suggest discussing with a subject matter expert to see how the clusters line up in real life. So if we had 3, most of them would fall into 1, and I think status type would reveal quite a lot to us. So cluster 1 is primarily photos. As we did see in our analysis, the number of photos and videos dominates the data set and almost creates 2 immediate segments. And between the 2, the number of likes and loves continues to segment them even more. It is a bit challenging to judge this elbow plot. Typically, you will see a sharper value. Perhaps it's at 6. Let's try 6. So what's happening here is when we have 3 clusters, the number of data points that are within 2 units of its centroid are 6,000. And if we try to increase our clustering to 6, we actually have fewer data points within 2 units of its centroid. So that tells me that 6 is probably too many. 5 is too many. 4 is too many. 3 has the best values. I would like to try 7 just to see what happens. What happened? Okay. Between 3 and 7, there is a change. 3 has 6,009 under 2 units and the max of 43 distance. And then if we have 7, we have the max of 41 distance and 6,068. So it could go either way, but if we have 7 clusters, it gets quite complicated, where we still do have a cluster dominated by photos, dominated by videos and statuses, and then the remaining clusters get these mixtures, but maybe that doesn't matter as much. Maybe there's some other input features that make a difference. Okay, and I would encourage you to continue the analysis of this data. If there are any questions, please feel free to leave comments in the video below. If you enjoyed this video, please like it and share it with anyone that might be interested. If you have any questions regarding today's tutorial, please leave a comment below and I will get to them. I mentioned that I would like to elaborate on time series analysis and date time wrangling in a future video, but I am also open to any of your suggestions for topics in data science and machine learning. To keep up with future videos that I post in these topics, please subscribe to my channel. All the materials for today's tutorial will be found on my GitHub, which is linked in the description below. And lastly, if you would like to support me in my efforts to grow this channel, you can check out the data science merchandise listed below as well. Well, thank you for watching, and I will see you in the next video.